Hi, this video is on sound waves, and it relates to Young and Freedman's University Physics, Chapter 16, the first section. Chapter 16 of Young and Freedman is on sound and hearing. This is my first video of 2017. It's January 2nd. Hello. Okay, sound waves. Now, if you're watching this video, there's a good chance you popularly know what sound waves are because you're listening to them. But what is sound? More technically, sound is a longitudinal wave, so not an up and down wave, not a transverse wave, but a longitudinal wave, which is a kind of a back and forth wave in some medium. Now, we normally think of sound as being in air, but you can have sound underwater, or you can have sound in a liquid, in a fluid. You can have sound in a solid even, as we'll see in the next video. The human ear hears waves somewhere in what's called the audible range, which is from about 20 cycles per second to 20,000 hertz. Now, because I'm 50 now, I'm not hearing those 20,000 hertz sounds anymore, much to my children's amusement. But anyway, frequencies that are above 20,000 hertz are called ultrasonic waves, and then those that are below it are infrasonic waves. So you know the old story that dogs can hear, higher pitches than humans can. They can hear some sounds that to you and me are ultrasonic. Okay, so you might remember some old wave business. So remember this equation, the basic wave equation, that it applies not only for transverse waves, but also for longitudinal waves. The y is a little funky for longitudinal waves because it's not an up and down y. It's more of a back and forth longitudinal y. But anyway, A stands for the displacement amplitude. That's the maximum displacement of material at any point. Because remember, the material itself doesn't travel. The material goes back and forth. The wave as a whole travels. The energy travels. But the actual materials only vary a little bit. So A is the displacement amplitude, the maximum displacement amplitude of that. And we're talking here again, when we're talking about sound, as a longitudinal wave. Okay, here's some things that are fairly commonly understood about sound waves, but let's connect them to the physics. So loudness. What is loudness from a physics perspective? Well, more on that in a second. But I wanted to get the easy stuff out of the way first. Loudness has to do with the greatness of what's called the pressure amplitude. The pressure amplitude is the big deal of this first section of the chapter. More on that in a second. But loudness has to do with how great the pressure amplitude is. So obviously, if it's a louder sound, then there's more pressure exerted on our eardrums. More on that in a second. Now, the frequency of a sound wave corresponds to something we call pitch. So, da 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 da. I varied the pitch. Da is a lower pitch, then da is a higher pitch. So the frequency of da is a higher frequency than da, which means that the sound waves are oscillating less at the lower note than they are at the higher note. Now, there's also something called timbre. Which, if you've done much with orchestra or with music, you know that the timbre of a sound has to do with kind of the richness of the sound. This is what distinguishes the same note on a violin and the same note on, say, an oboe. It may be the same note in terms of the frequency, pitch, but the harmonic content is different. My voice is giving off a superposition of multiple waves in harmonic content. So my voice has a certain timbre. That's how voice recognition software would basically analyze the harmonic content of my and because my vocal cords have a certain definable timbre, you can analyze and know that it's me. Allegedly. I've never done this. So that's called harmonic analysis, when you kind of pull apart the individual waves that have been added together, that have been superposed on each other. That's also called Fourier analysis, as we said in the last video from the previous chapter. Okay, so timbre has to do with that varied harmonic content. Of course, noise is just a kind of a random combination of all frequencies. White noise is like psst, I've just thrown in all the frequencies in there. And so it's a kind of chaotic superposition of a mess of gray junk. Okay, so there you have kind of the easy stuff from the chapter. Now, sound waves can also be described as variations of pressure in a wave-like fashion. So the pressure goes up a little, the pressure goes down a little, the pressure goes up a little, the pressure goes down a little. That kind of in a way that you could actually analyze as a sine wave. And in fact, how do our ears hear? Well, you have, if you know the structure of the anatomy of the ear, and there's a diagram in Young and Freedman. So we have these tubes that come up from our kind of nasal and throat passages. They're called eustachian tubes, and they come to one side of the ear, and then of course the sound goes in this part and hits our eardrums. And so the difference between the pressure, so there's kind of a constant or absolute pressure in our eustachian tubes, and then you have these sound causing variation, causing variations of pressure on our eardrums that hit and then the hammer, the anvil, the stirrup, and then the cochlea, which has fluid in it, and there's a example of that in this section. So if you remember from the chapter on fluid mechanics, gauge pressure is the difference from the air pressure or the normal pressure, the absolute pressure. And so basically the pressure we're talking about here is a gauge pressure. It's a difference in pressure. It's a variation in pressure from the air around us that is helping us sense sound. And so that's how we hear. We hear because the eardrum senses these changes in pressure from the normal pressure or the absolute pressure coming up from our eustachian tubes, and then our brain knows how to decipher that, how to decode that, as it were. Okay, so what is the pressure amplitude? The pressure amplitude has to do with the change in pressure, because just like the wave changes in amplitude, the pressure changes in amplitude. Do you remember the bulk modulus from, I think it was chapter 11? The bulk modulus, first of all, bulk pressure has to do with pressure that's coming from all sides. So we did several different kinds of pressure back in chapter 11. There was shear, the shear modulus, or the shear pressure, and different kinds of pressure. So here we're talking about bulk pressure, where the whole of something is experiencing pressure. And the bulk modulus is the ratio of the bulk pressure to the bulk strain. Strain is how much the size changes. So the bulk modulus is the ratio of the bulk pressure to that bulk change in volume. Or to put it, we can put it like this: the bulk modulus equals the negative of the pressure, bulk pressure, over the change in volume, the infinitesimal change in volume. And the reason it's negative is because the change in volume is going to be negative, and so to keep the bulk modulus positive, we have a negative in the top to counteract the negative in the bottom. Okay, so you don't have to remember all that. I mean, the main thing to remember is where we end up. So this is where we end up, and Young and Freedman do some nifty algebra to get here. You don't have to know it, but let me just try to walk you through it a little bit. So the first thing they do is they isolate the pxt, and to do that, they of course put the negative on the other side and multiply the other side by dv over v, and so we have negative dv over v times b on this side equals the pressure function. There's the b from that part. What about the rest of this? Well, dv slash v instantaneously is basically the partial derivative of y. Let me go back to this. if you take the partial derivative of y xt, that gives you basically the instantaneous dv over v. And so if we take the partial derivative of this with regard to x, the derivative of the cosine of x is the negative sine of x. So it becomes negative a cosine, and then we're doing it with regard to x, so that means this all becomes a constant and it disappears, and we're left with k. So the partial derivative of y with regard to x is negative k a sine of this. So when we go back here, again, you don't need to know this necessarily, I'm just explaining it. So there's the k, there's the sine of this, and then the negative, you remember I had a negative, so the negative and the negative cancel, and so that's where this equation comes from. Okay, you don't need to know that necessarily, but this is the equation that you need to know. And when sine of this equals 1, that's when this is at its maximum. So the pressure is at its maximum basically when the sine becomes 1. And this is, right here at the bottom, the pressure amplitude. And there you basically have the first section of chapter, what chapter is it? 16? Yeah.